The objectives for the coming segments are as follows. We will introduce and use vectors. Vectors enable more than a single bit to be used with a wire or reg quantity. There are a number of ways in which the bits in a vector can be used, and the different ways will be introduced with examples. A gate-level example of a 4-bit comparator will be modelled in Verilog. This will use simple gates and combine hierarchical design with vectors to model a real design. In the Verilog language, up to now, we've only been able to declare a single bit of type reg or of type wire. It's possible to declare groups of bits and to work on those groups using what's known as vectors in the Verilog language. The following definition comes from the language reference manual. A net or a reg declaration without a range specification is considered a 1-bit wide quantity and is known as a scalar. Multi-bit, net and reg data types shall be declared by specifying a range, which is known as a vector. And this is what we want to focus on in this segment. So for example, if you want to have 4 wires, you could declare them as 4 individual wires or use a vector to collectively create the 4-wire group. If you want 4 bits with 4 reg variables, you could do that with 4 separate declarations or use a single declaration to create a 4-bit reg variable. The term scalar and vector in this context has nothing to do with the physics definition for the scalar and vector. Here are some example declarations when declaring vectors. If we contrast this, for example, with a declaration for a scalar quantity, here A is a reg variable and can store a single bit and is labeled with the identifier A. So we can only store a single bit inside this space here. When we define a vector, we still specify the type, whether it's a reg or wire. We include an identifier. And in the case of a vector, we specify a range. We use square brackets and 2 integers separated by a colon. So for example, if we've got the integers 3, 0, this indicates that we have bits going from 3 to 0 inclusive, so we've created a 4-bit quantity. So AV now looks like this. 1, 2, 3, 4. And we can store 4 bits in AV, and each space here can hold a single bit. When we talk about a bit, we're still using our 4 value set containing 1, 0, X and Z. So each bit can be one of those 4 values. If we take the data bus declaration, it's declared to be an 8-bit quantity of type reg. And you can see here we've got 8 bits for data bus. And because it's of type reg, each box indicates storage for a single bit. If you take the wire declaration, control is of type wire and our range goes from 3 to 0, indicating that we've got 4 wires. So over here you can see that the 4 wires are identified by control. And for each example, you can see that we've a range indicating the size of the vector. So 3 to 0, 7 to 0, 15 to 8, which is an 8-bit vector, and 8 to 15, which is also 8 bits. So you'll note for this first case, 8:15, we start at 8 and go up to 15. In the second example, we start at 15 and go down to 8. Start at 7, go down to 0. Start at 3, go down to 0. And the first integer is used to indicate the most significant position. So for our first declaration, address upper A, the bit position 8 is the most significant bit. The first integer indicates the most significant bit position. In this example, 15 is the most significant bit position. In this example, 7, and in this example, 3. So you can see you've got a choice as to go from a lower to a higher value or from a higher to a lower value. The standard convention is that we go from high to low. While both are allowable, it becomes confusing if we mix the two possibilities. So in Verilog, it's normal practice not to use this form. And there are situations where it turns out to be useful to use a lower bound that's not 0. So in these two examples, the lower bound is 0, and in this example, the lower bound is 8. And if you look at these two range specifications, both provide us with a range of 8, which indicates that address upper B and data bus both store 8 bits. And for our work this semester, it's normal practice to use the lower bound of 0. And that means to create an n-bit vector, we go from n-1 down to 0. And a term that's normally used for vectors with digital designs is the term bus. So a bus is a group of signals that's generally referred to with a single name. So for example, control here, we could call that the control bus containing 4 wires. We have data bus representing an 8-bit reg variable. To summarize, to declare a reg vector, you do so using the reg keyword, space, square bracket, integer, colon, 0, close square bracket, and space followed by an identifier. In this case, sum is a 5-bit reg variable, and if you want to declare more than one 5-bit reg variable, you can just list further identifiers separated by commas and terminate with a semicolon. So in this example, we have sum with 5 bits, and we've total with another 5 bits. Now that we've seen how to declare vectors, let's look at using them by considering bit selection. Individual bits can be accessed within a vector by specifying the position using an integer value. For example, if we take databus, which is an 8-bit reg variable, and control, which is a 4-bit wire. This is what it looks like. We've got 8 bits of storage for databus, and we've got 4 wires for control. An example usage involving bit selection is the statement shown here. It's an assign statement which drives a wire in the control bus. And if you look at the data bus, it's an 8-bit reg variable, and the bit positions are specified as bit position 0, bit position 1, up as far as bit position 7. So bit position 5 refers to this particular bit, and that value is on the right hand side of the assignment. So that's the value that drives the wire on the left hand side. And on the left hand side, the wire is the bit specified by bit position 2 of the control vector. So control is a vector and it's a 4-bit wire. Bit position 2 refers to this wire. And the effect of our statement is that we drive the value in this bit onto this particular wire. Now the use of the square brackets for selecting a bit position looks very like an array access that you would have seen in Java or the C language. It's important in Verilog not to think of this as an array access, as later on we will see arrays in Verilog. And when we deal with vectors, it's important not to use the word index, which we use when accessing arrays. We use the term array indexing. This is actually bit selection. So think of it that way, because later on we will see array indexing, which is different from bit selection in Verilog. So when accessing an individual bit within a vector, we use the vector name, for example, control, square bracket, an integer value, and close square bracket. And this is a way in which we can access an individual bit or an individual wire within a vector. What happens if the integer that we use for the bit selection is outside the range specified in the declaration? In the case of control, the range is specified as going from 3 to 0. This indicates that we can only use the values 0, 1, 2 or 3. In the case of using a bit select outside the allowable range, or if the bit select is an X or Z, so this could be an X or Z in addition to an integer, then the value returned by this reference will be an X value. And depending on the tool that you use, sometimes a warning is given when this happens. So for example, a bit select into vect A is out of bounds is a warning that occurs when a design is loaded for simulation. The value between square brackets must be an integer, but it can be an integer expression. It does not have to be a constant. So for example, we could have assigned control bracket I close bracket, where I is an integer. But for the coming weeks, we'll normally use an integer constant when accessing a bit within a vector. The example shown here drives a value onto the wire at bit position 2. If we want to update a quantity inside the data bus, because the data bus is of type reg, one way to do this is inside an initial construct. So we could have the following: data bus bracket 3 is equal to 0. When the simulator executes this statement, it places the 0 value into the 4th bit position. So remember, the bit positions start at 0, so data bus with the bit select 3 refers to the 4th position in our data bus. Another example: data bus with the bit select 2 is equal to control with the bit select 1. And this has the effect of taking whatever value is on the wire, this particular wire, and placing this value into the bit at bit position 2.